Okay, I'm recording now. Okay, perfect. All right, so I mean, just to remind you first, we discussed, as I said, binomial distribution or binomial experiment. And in a binomial distribution, we said the variable is R, right? The number of successes is given by the variable R. And the variable R has a finite number of values. And that's why it's a discrete variable, right? So just to remind you, so in a binomial distribution, in a binomial probability distribution, so the variable, our variable X is actually R. So the variable is the variable X is given by R. So that's the number of successes, right? R, and which is the number of successes, right? And so the number of successes, it's because we have a finite number of trials. So then the number of successes is finite. So R, this variable R, so R has a finite number of values. Right? I mean, R, goes from, let's say, if you have, let's say, 6 trials, then R would be, goes from 0 to 6. So R would be equal to 0 or 1 or 2 or 3, etc. But so it goes from 0 to 6, right? If you have like 6 trials, etc. So that's a finite number of values. So that's why R is a discrete. So R is a discrete random variable. So it's a discrete variable, right? Because it has finite number of values. And then we said for the graph, just to remind you, the graph of a binomial distribution. So for the graph, we had like the graph of a binomial distribution. We use the histogram to graph a binomial distribution, and we had something like, you have your this is your R, your variable R, your horizontal axis, etc. And then you have your histogram. For example, your histogram can be something like this here, right? For example, and then we said what's an important remark here is that the area under the graph is 1, right? We said area under the graph is equal to 1 or 100%. Okay. Anyway, so that's for our binomial distribution, which is, as I said, its variable R is discrete, right? Now, so in this chapter, we're gonna study normal distributions. So normal distribution, I guess it's one of the most important continuous probability distribution. So the variable X in a normal distribution is actually, it's a continuous variable. It's not discrete like in a binomial distribution. So so today we're gonna discuss normal probability distribution. So normal probability distribution. Okay, and so as I said, it's one of the most important continuous probability distribution. So first, the variable. So the variable X. So the variable X in a normal distribution is continuous, Okay, so it's not discrete like in a binomial distribution. So it's continuous, which means that x, x has infinite number of values. Okay, not finite number of values. So x, the variable x has infinite possible values. Now, infinite number of possible values, values. All right. So, for example, I think a very simple example would be example. Let's say x, the variable x. Variable x is let's say it's the time to get on campus. Okay, and you hear me, guys, right?
Yes.
You hear me? Yeah, okay.
Yeah.
Okay, thanks.
Yes.
Yeah, so I said this variable x, for example, it's the time to get in campus. Let's say you live in the Bronx, and usually you need, let's say, between let's say 0 and 3 or 0 and 2 hours, okay, to get on campus. So let's say x, x is a number between 0 and 2 hours. Okay, so like on your number line, this is 0, this is 2, and so your variable x can be any value between 0 and 2, right? So x belongs to this interval, 0, 2. Okay, so it can be any number between 0 and 2, right? So for example, x can be a decimal. X can be equal to, so for example, x can be 1.075 hour, or x can be like 0.972 hour, etc. So between 0 and 2, guys, there are infinite number of real numbers, right? So if you pick a point here between 0 and 2, right, that will be, it can be a decimal, of course, can be a fraction, and there are infinite numbers, number of numbers between 0 and 2, right? Because of the decimals, right? Because of the decimals, you have infinite possible values for x, right? So this is different from R. Like R in the binomial distribution, remember R, the number of successes, like if you have, as I said, like 7 trials, then your variable R is can be equal to 0, 1, 2, 3, 4, 5, 6, 7. That's it, right? So it's just 8 possible values, right? Here, like x, when x is the time to get in campus, it can be any number between 0 and 2. Okay, it can be a decimal. So that's like you have like infinite number of possible values, right? Because of the decimals. All right. So that's the first thing about normal distribution. So the variable x, it's a continuous variable. It's not a discrete variable. It's continuous, right? Now, the graph or the curve of a normal distribution. So this is the first, let's say this is like the first property of a normal distribution. The variable x is a continuous variable. Second property of a normal distribution is that the curve or the graph, so the graph of a normal distribution is actually bell shaped. So the shape of the graph looks like a bell. Okay, and the highest point of the graph is at the mean. And the highest point of the graph is at the mean mu. Okay, so the graph of a normal distribution is going to look like, as I said, it's a bell shape. Oops. So the graph is going to look like something like this here. Okay, so here, of course, the horizontal axis, that's the x-axis, right? This is your x-axis. Okay, and so the highest point, as I said, the highest point of the graph is going to be, let's say this is like the highest point of the graph, so it's going to be at the mean. So here you have like the mean, right? And of course here, let's say here, this is like mu plus 1 standard deviation. This is a mu plus 2 standard deviations. This is a mu minus mu minus 1 standard deviation, and here it's like mu minus 2 standard deviations, etc. But anyway, so the point is the highest point of the graph is at the mean. So here, of course, sigma, this is sigma here is the standard deviation. Okay. One more thing, guys, about the graph is that you see here the graph. You know, when the graph or the curve approach x-axis, and actually it doesn't touch. It never touch the. It doesn't touch the x-axis, right? It gets as close as you want from the x-axis, but it never touch the x-axis. So here there is no intersection. The graph of a binomial distribution. Oh, sorry, the graph of this of the normal distribution. It doesn't intersect the x-axis. So here there's no intersection with the x-axis. So here also there's no intersection. So it gets as close as you want from the x-axis, but it doesn't intersect the x-axis. Okay, so here no intersection. And what's really important about the graph? So why the graph is is very useful, because the graph of this binomial normal distribution, of course, is gonna give you the probability. So the idea is that so this is say property number 3. So if you have the graph of your normal distribution, so this is my normal distribution. Okay, this is my normal distribution, the graph of my normal distribution. Okay. So what you need to understand, guys, is that the area, so if you have like some value of, let's say this is your x here. Okay. And so let's say we have some number here. So for example, let's say this is 10, okay? Then the probability that the variable x is less than 10 is less than 10. That will be the area to the left of 10. So that the area under the graph to the left of 10. So you see here this area on the left of 10, the area of this region, this green region, okay? So the area of this region, that will be the probability that X is less than 10. Okay. So that's the area of the green region. So this is, again, this is the area on the left of 10. This is the area on the left of 10. So the probability that X is less than 10, that'll be the area on the left of 10. But what you need to keep in mind again, guys, is that the area under the graph, so this is like the graph for binomial distribution. The area under the graph is equal to 1. Okay, so you need to keep in mind that the area under the graph is 1 unit square, is equal to 1. Which is 100%. Right? So this area of this, the area of this green region, which is the area on the left of 10, will be less than 1, right? Because, you know, the total area is 1. So the green, the area of the green region, of course, is going to be less than 1. So that's why it's a probability, right? And so in general, like if you have like two numbers, so again, this is my, here's my normal distribution. And let's say we have two numbers. Let's say this is 5 and 10. Okay. Then the probability that the variable X, for example, again, like X is the time to get in campus, right? So the probability that the time to get in campus is between 5 and 10, let's say 5 and 10 hours or wherever. So X is between 5 and 10. That will be the area of the region under the graph between 5 and 10. So like this is 5, this is 10. And the area of this region between 5 and 10, that's the probability that your X is between 5 and 10. So this is the probability that X is between 5 and 10. Okay, so this is the area of the region, the area between 5 and 10. So this is why, I mean, the graph of the binomial distribution is really important, right? Because from the graph, you can get your probability. All right. So yeah. Now, so for this normal distribution, we have like a sort of Chebyshev theorem. So just to remind you, what's a Chebyshev theorem? You know, for any distribution, with the Chebyshev theorem, you can get like the smallest proportion of data that lies like within 2 or 3 or 4, etc., standard deviations from the mean, right? So for normal distribution, actually, we have better results than the Chebyshev theorem. So for normal distribution, so this is a theorem. So again, this is a better approximation, right? Of a better approximation of the Chebyshev theorem. Okay. So for a normal distribution, we have actually the following. So for a normal distribution, we have so we have the following. So let me just graph my normal distribution. So let's say this is the mean. Right, and then this is mu plus sigma. This is mu minus sigma. This is mu plus 2 sigma, mu plus 3 sigma. It's minus 2. This is mu minus 3 sigma. Right, so again, the mu, that's the mean. Right, and sigma, that's the standard deviation. So what we have is the following. So here, so we have your mean, right? And so it turns out that the area between the mean and the mean and the mean plus sigma, this is actually 34% or 0.34. Between mu and mu minus sigma, it's also 34%. And then between mu plus sigma and mu plus 2 sigma, this is actually, I think, 13.5%. Here, it's also 13.5%. And then here, I think we have like 2.35%. And this is also 2.35%, etc. So, for example, you know that, so consequence of this graph, so you know, for example, that 68%. So, for example, you know that's approximately 68%. 68% of your data values belong to the interval mu minus sigma, mu plus sigma. Okay, that's because, you know, as you can see here, so in this graph, between mu minus sigma and mu plus sigma, so this is mu, the mean, and this is mu plus sigma, and this is like mu minus sigma, right? We said the area of this region is 0.34, 34%, and this one here, it's 34%, right? So the probability that your x, your variable x, is between, you know, mu minus sigma and mu plus sigma is actually equal to the area between these two numbers, right? It's the area between mu minus sigma and mu plus sigma. Now, what's the area between mu minus sigma and mu plus sigma? So this would be the area, right? So this is like 34% plus 34%, right? 34% plus the other 34%, right? So that's 68% or 0.68, right? So the probability that your data value is between mu minus sigma and mu plus sigma is actually 68%. So what we are saying is that 68% of your data values, they belong to this interval mu minus sigma, mu plus sigma, right? And you can do the same with, for example, so here we have a lot of consequences actually. So this is the first consequence. Another consequence, for example, is that you know, if you take the interval, what will be the probability that x is between mu minus 2 sigma and mu plus 2 sigma? Well, so I'm gonna just graph again so you can see it. Here's my graph. This is my mu. This is my mu minus sigma. This is my mu minus 2 sigma. Right, this is mu plus 1 sigma, and this is like mu plus 2 sigma, right? And then we have, this is 34%. This is also 34. Now, next here, we have like 13.5%. And next here, this is also 13.5%, right? Now, what's the area of this region between mu minus 2 sigma and mu plus 2 sigma? The area of this region. Any guess? So that will be the sum, right, of the areas. So the first area would be 13.5% plus. So this is my first area. Second area, this is actually 34 plus another 34 plus another 13.5, right? So the probability that your x, your variable x is between mu minus sigma and mu plus 2 sigma, it's 68 plus 27, which is 95%. Right. So what we are saying here is that approximately 95% of your data values, they belong to the interval mu minus 2 sigma and mu plus 2 sigma. So approximately like 95% of your data values. So the probability that your data value is between mu minus 2 sigma and mu plus 2 sigma is 95%. It's 95% chance that your x is between the mu minus 2 sigma and mu plus 2 sigma. Belong to the mu minus 2 sigma, mu plus 2 sigma, right? So just a reminder, like for Chebyshev, in the Chebyshev theorem, guys, I don't know if you remember, what's the probability that the smallest proportion of data that lies within like 2 standard deviations from the mean? Remember, it was 75%, right? And the Chebyshev theorem, Chebyshev's theorem, we had like 75% of data values, between mu minus 2 sigma and mu plus 2 sigma, right? And here it's better than, it's much better than 75%. It's actually 95% of the data values between these two, the mu minus 2 sigma and mu plus 2 sigma, right? Etc. So you can, of course, you can do the same thing for mu minus 3 sigma, mu plus 3 sigma, etc. Let me just say one more thing before the exercise. So we also know that like the mean actually divides your graph into 2 equal parts. So the area of this region here on the left of the mean, that will be 50%, right? And the area on the right of the mean under the graph, of course, it's also 50%. Okay, so keep in mind that the mean divides your graph or the area of the under the graph into like 2 equal parts, right? The area of each part, of course, is 50%. All right. Any questions so far, guys, before the exercise? Let me see the chat. Nope. Okay. So all right, so let's exercise. So let's practice a little bit. So exercise. So, okay, so we have the incubation time. For Rhode Island red chicks. Rhode Island red chicks is follows, so the incubation time follows a normal distribution. Okay, with mean mu equal to, so the average is 21 days, and standard deviation sigma is equal to let's say 1. Okay, 1 day. All right, so let's say you have 1,000 eggs. So if 1,000 eggs are being incubated, how many chicks do you expect will hatch? Will hatch in, let's say, so 1. So 1 in, let's say, 19 to 23 days. In 19 to 23 days. All right. 2 in 21 days or less. And 3, let's say, in 18 to 22, let's say, days. And last one. Uh, 4 in, let's say, more than 22 days. Okay. All right, guys. So what I'm gonna do, I'm gonna go over this exercise. We're gonna do it together. Okay, I'm gonna try to explain how to answer such a problem, right? And then I will give you probably 1 or 2 similar problems or similar exercises. All right. So I'm gonna first explain how to, how to answer such a problem. So let's read this again. So incubation time for Rhode Island chicks follows a normal distribution, right? This is so a normal distribution here is like a keyword with a mean, of course, is 21, and standard deviation sigma is 1, right? And we have like 1,000 eggs, etc. So how many chicks do we expect will hatch in 19 to 23 days? Okay, so of course I'm gonna try to use the graph I had. The graph I had for my normal distribution. Just to remind you. So, I have my, let me just first graph. So, I have my mean. So what's the mean in this problem? The mean, the mean we said it's 20, where is it?
21.
It's 21 days, right? Thank you. 21 days. So here's 21 days. That's my mean. All right. And then, of course, you have the mean plus 1 sigma, the mean plus 1 standard deviation. So standard deviation here, it's 1, right? Sigma is 1. As you can see, standard deviation is 1. So mu plus sigma, 21 plus 1, that will be 22. So this is like 22. And then we have like, 23, which is like mu plus 2 sigma, etc. And then on the left, we have like mu minus sigma. You subtract 1 sigma. That's 21 minus 1. So that's 20. Then you have like mu minus 2 sigma. That's like 21 minus 2. That's the 19. And let's say here, this is 18. This would be like mu minus 3 sigma. Okay. Now, what's really important is that the areas under the regions, right? So for example, here we said like between mu and mu plus sigma, this is 34%. Between mu and mu minus sigma, it's also 34%. Right? Between mu plus sigma and mu plus 2 sigma, we said it's 13.5. Yes. So this is like 13.5%.
Professor, so
Yes.
this numbers, the 34%, the 13.5%, is that the same number that we always use, or this is just based on this
It's
example?
always, for always for a normal distribution. Whenever you have a normal distribution, that's like the areas of the regions between between your mean and your mean plus some number of standard deviations. Yes, that's always in numbers used for normal distribution. Yeah.
Okay.
Here it's 13.5, and here I think it's like 2.35%, right, etc. Anyway, so what we need in the first question is 19 to 23, right? So what's the probability that your incubation time, right? So for number 1, we are looking for the variable here, of course, it's the incubation time, right? It follows the incubation time follows normal distribution, right? So my variable x, it's the incubation time. That's the variable. It follows the normal distribution. So my variable x was the incubation time. So in number 1, we need x to be my incubation time between 19 and 23, right? So what's the probability that x is between 19 and 23? Okay. Again, x, this is the incubation time. So this is like the probability that the incubation time, it's between 19 and 23. So as I said, so because it's a continuous probability distribution, I mean, the variable x is a continuous. So then this probability is actually the area of the region between the 19 and 23, right? So between 19 and 23. So here's 19. Here's 23. So this probability would be actually corresponds to the area of this region, this green region, right? That's the area between 19 and 23. Now, let's try to compute the area of this green region. So first we have, like here, we have 13.5. And then we have like 34, and then 13.5, right? So plus 34, plus another 34%, of course, plus another 13.5. So the total would be 95. So it's not, yes. Any question? No? Okay. So the total is 95%. Okay. So we expect that 95%, okay, of the chicks will hatch between 19 and 23 days. Okay, so we expect So we expect 95% of the chicks will hatch, between 19 and 23. Between 19 and 23 days. Right now, of course, I have. So how many? How many? We have 1,000 eggs, right? So if we have 1,000 eggs, we know that 95%. Sorry. So 95% of chicks will hatch between 19 and 23. So that's like 1,000 eggs. So we expect. So 1,000 eggs, 95% of the 1,000 eggs, 95% of 95% off. So when I say off, that's a multiplication, right? Off the 1,000 eggs. All right, so that will be equal to 950. Okay, so we're gonna have 900. We expect that 950 chicks will hatch between 19 and 23 days. Does this make sense to you guys? Any questions?
Yeah, I have a question.
Yeah, please.
Going back to the graph, you added for the mean, you added 21 plus 1 because that was the
20.
the mean. Yeah, over here.
Oh,
the mean is
yeah, the mean.
21.
Yeah,
You added
the
you
mean.
added, yeah, you added 1 and it gives us 22, 23.
Yeah.
But over here you said that the mean plus 2. Well, I don't understand the 2 on right
here.
Yeah, there.
Yeah, it's a mu, which is 21 plus 2 times 1. Sigma is 1, right?
Oh, sigma is 1. Okay.
2 times 1, that's 23. I mean, mu and sigma both are given, right? We know.
Yes.
It's given, are given, right? I know mu is 21 and sigma are 1. So mu plus 2 sigma, that's like 21 plus 2 times 1.
Okay.
That's okay. 20.
Okay, get it now. Thank you.
Any other question, guys? All right. So then, what about number 2? So number 2, it says in 21 days or less. In 21 days or less. So any guess what will be the probability that the incubation time is less than 21? Right? When I say 21 days or less, it means like less than 21 days, right? So your incubation time, oops, sorry about that. So your incubation time is, which is a variable x, is less than 21, right? Or less or equal to 21, okay? So again, x, that's your incubation time. That's your variable. All right, so now let's take a look to the graph. And what would be the probability that x is less than 21? Any guess?
Is it 47.5?
Nice try.
Oh, wait. I missed one. I missed one.
Actually, no. What do we have to? What we have to understand, guys, is that actually, you see this graph here is gonna continue, and it's gonna get as close as you want from the x-axis, but actually, it never touch the x-axis. Okay, so it's gonna be very, very close to the x-axis, but it's gonna never intersect the x-axis. The same here on the right side. It's the same thing. It's gonna, so the graph is gonna continue like this, and it's gonna get as close as you want from the x-axis, but there will be no intersection. Okay. Well, we need x to be less than 21. So x less than 21 that will be the area of the region which is on the left of 21, right? Your x is less than 21. So you need the area of the region which is on the left of 21. So you need, let me just graph again here so we can understand. Otherwise, if I use the same graph, it's going to be a mess. So this is your mu, which is of course 21, right? So when I say x, probability that x is less than 21, so it has to be the region, that's the area of the region which is on the left of 21. The whole region. Okay, you cannot just stop at, I think Asamta, your suggestion is to to add this 34 to this 13.5 to this 2.35, right? But then still you have like, you see this region here?
Yeah.
You're missing some region here.
Okay.
However, the thing is, just to remind you what I said about the mean. Actually, the mean divides your graph into two equal parts. So like the area of this region here on the left, that'll be 50%. And the area of the region on the right of the mean would be 50%. Okay, so you think of the mean as like the center. It's like so the graph is like symmetrical about the mean, right? Your mean is like the center of the graph. So we have like 50% on the left and 50% on the right. So the probability that x is less than 21, less or equal to 21, is exactly 50%. It's the left of 21. So on the left of 21, we have 50%. Okay, so this is 50%. Okay. So you see how it works. So the whole region on the left, it's actually 50%, and the region on the right of the mean, it's also 50%. So of course, we expect 50% of the eggs. So 50% of 1,000 eggs. So that would be, of course, 500. So expect 500 chicks will hatch in less than 21 days. All right. Please let me know if you have any question, guys. Please interrupt me. All right. Now in 18 to 22. All right. So 1822. Well, from the graph here, well, here's 18, right? And here is 22. So I need the region between 18 and 22, right? So between 18 and 22, I have 2.35. Let me probably use another different graph. So for number 3, this is the probability that your x, the incubation time, is between 18 and what was it? 18 and 22, yes, 22. So 22. So again, my graph. This is your mean, which is we said it's the mean was 20. This is 20 plus 1. This is 34%. This is 19. This is another 34%, right? And then you have 22, which is 13.5%. Then, right, between 18 and 22, right? Let me just make sure that, yeah, 18, 22. Oh, sorry, the mean is 21. Sorry, the mean is 21, it's not 20. Sorry for that. So the mean, the center, it's 21. Right, so this is 21. This is the mean. So this is 22, 23. and then this is 20, this is 19, and this is 18. So we have here, this is 13.5, and then we have 2.35, right? So yeah, we need the region between 18 and 22. So the region between 18 and 22. So this is 18, this is 22. So the probability that your x is between 18 and 22, that will be equal to, well, first we have the 2.35% plus 13.5 plus the 34 plus another 34. Right, that's 68, 68, 78, 81, 83, thank you, 83.85%. Thank you. Okay. So then, of course, the number of the chicks that would hatch between 18 and 22. So we expect we have 1,000 eggs, of course. So this is 83%.85 off the 1,000 eggs, right? Sorry. So that'll be equal to, of course, 838.5. So chicks would hatch between 18 and 22 days. Right? Last one, I think there's one more, number 4, in more than 22 days. Okay, this is nice. This is good. A nice question. In more than 22. So for number 4, it's more than 22. So we have like, again, so the mean is 21. Then you have mu plus, I mean, the mean plus sigma is 22. So we have like, this is 34%, right, etc. This is, here is 20, this is another 34%, etc. Anyway, so we are looking for probability that x is it's more than 22 days, right? So x is, it's larger than 22 days. Okay, so this is more than, x is more, is larger than. So more than 22, the probability that x is more than 22, so that's the region on the right of 22. So the corresponding region would be this one here, on the right of 22. Right? If it was less than 22, then that would be the region on the left of 22, right? Here, it's more than 22. So if it's more than 22, that's the region on the right of 22. Okay. Now, any guess what will be this probability that x is larger than 22? What will be the area of the green region here? If you try to use some basic, basic geometry. So what do you need to keep in mind, guys? Remember what I said, that the mean,
it's half.
It's like the center, yeah, the half of your it's like the center of your graph. Like on the right of the mean, you have like 50%, and on the left of the mean, you have like 50%, right? So what will be the?
Professor, I'm thinking, will it be 50? But you said that it's
no, it's not 50.
It's not 50 because it's after 22 though.
Yeah,
that's what I was thinking.
It's after after 22. The 50, it's after 21.
Yeah. Okay.
So then after 22, what would be the area? If after 21,
Mm-hmm.
if after 21 it's 50, but we need
Mm-hmm.
after 22.
So is it like 45?
Excuse me?
Okay.
30, 35, you said?
I said 45.
Ah, 45. No. Okay, so the idea is that, let me use a different color. Let's use yellow. So you see the yellow region here? The yellow region? The yellow is 50%, right? The yellow region here, it's 50%. Okay, but you know that this region between 21 and 22, this is 34%. Okay, and you need this one here, right? So what's the difference? That's the difference. That's the difference between the 50 and 34.
16. 16.
16. Yes, 16.
Yeah.
Yes.
16. Okay.
So this is 50 minus 34. So that's 60%. So this is the difference between a difference. A difference between between the 50 and 34%. Okay. So I mean, this 50%, it's like another piece of information you can use, right? Like here, because after, well, between 21 and 22, it's 34. Between 22 and 23, I think it's 13.5, and then between 23 and 24, it's like 2.35. But then after that, I mean, I didn't give you any other number, right? So after that, it's like unknown, right? But the thing is, that the area of the region on the right of the mean, it's 50%. So yeah, so that the green region will be just the difference between 50 and 34. All right. How much time is left? Any questions so far, guys? So you see, I mean, and we get in the next section, we're gonna compute more areas actually, because the thing is, in this problem, the areas here, they are just for the areas of the region between, like, between mu and mu minus sigma, or mu and mu plus sigma, etc. But the problem is, so what about, I don't know, if you take another random number? So what about, for example, probability that x is, let's say, larger than 21.5 days, half of a day, right? 21 and half of a day, right? I mean, the problem here is that, this 21.5, it's not like, it's not equal to your mean plus, plus 1 sigma, or your mean plus 2 sigma, right? So this is like 22, this is like 23, right? So it's not a combination of the mean and the standard deviation, right? So the anyway, so the answer to this is going to be next sections. Right. So this is not, so what I'm saying, this is not, it's not 21 plus 1 sigma, or 21 plus 2 sigma, right? Anyway, so okay, so we have like 10 minutes left. So let's do one similar problem.
Professor,
then, yes,
when you
yeah,
said
please.
this next section, what do you mean exactly? So you need to go up to 22, or?
No. What I'm saying here is, like, we can answer, we can find the answer for, like, when your incubation time is like 21 or 22 days or 23. Let's say a whole number. But what about if you pick, because your incubation time, it can be decimal. That's like, by definition, your incubation time, it's a normal distribution, so it's a continuous variable. So it can be decimal, right? You can take instead of 21 or 22, I can take 21.5 or 21.75. You know, it can be any number, you know, in your interval. It doesn't have to be like a number. So
Okay.
it's not like a combination of your mean and the standard deviation. So
Okay.
yeah. So for random values, that's what we're gonna do at the next section. So we're gonna try to find the corresponding probability.
Okay.
Okay, so in the last 10 minutes, I mean, time really goes really fast. I mean, this is incredible. But anyway, so here's an exercise. And if we don't finish this exercise, if I don't have time to, go over this exercise, but I will try to my best to do it next time. But otherwise, I will start. We'll start a new section. But another exercise. So let's say the age of the students in BCC follows a normal distribution with, let's say, the average mean, the average of the average age of students is, let's say, 21 years. Okay. And with standard deviation sigma is half of year, so 0.5. Right. So yeah, what's the percentage, or what's the probability or the percentage of students with age first, let's say between 20 years and 21.5 years. To less than less than 20.5 years. 3, more than 21 years. Okay, and last one for fun, number 4. Let's say between between 21 and let's say 21 and 22 years. So of course the idea, guys, let me just write down, because I mean we have like 6 minutes, so I don't think you're gonna have time to finish this exercise. But again, the idea is, of course, to use our the graph of the normal distribution, just to remind you. So of course, like here in this problem, so we are interested in the age of the students, right? So the age of the students, of course, would be your variable x. So this is your variable x, and it follows, of course, a normal distribution. So yeah, so the idea is to use this graph right here. So you know your mean is 21. like the center of the graph is 21, right? And then you have your standard deviation is 0.5. So here it's 21 plus 0.5, that's 21.5. And here we have 34%, right? This is mu, and this is mu plus sigma. Here it's 20.5. That's like mu minus sigma. This is another 34. Now, plus 2 sigma. So mu is, again, mu is 21. Plus 2 sigma, that's plus 2 times 0.5, so that's plus 1. So we have 22. So this is mu plus 2 sigma. Right, and here, of course, we have 13.5%. And here it's 20. That's mu minus 2 sigma. And that's another 13.5. What else you need here? Yeah. Actually, that's all you need to answer the 4 questions. And of course, you need to keep in mind that the mean divides the graph into 2 equal parts with 50% each, the area of each part. So this is also 50%. Okay, well, we have like 3 minutes. So I'm gonna just answer the first question, guys. You can think about this exercise, and then I'm gonna finish this next time. So we're gonna meet this Wednesday. We do have a class with this Wednesday in person, of course, the usual time. Okay. So let me just say, so for example, for number 1.
Hi, did you get the attendance for today? Kathleen speaking,
Yes.
by the way.
Yeah. Okay.
Okay.
I got you. I got you.
All right,
Thank you.
because I'm about to get on the train, so I have to leave the class.
No problem. No problem.
Okay, bye. See you
on
Wednesday.
Wednesday. Take care.
All right.
So yeah, guys. So for number 1, so you need the probability that X, the age of the student, is between 20 and 21.5, right? So that will be the area of the region between 20. So here's 20 and 21.5. So here's 21.5. So you need the area of this region right here. Right, so that will be, oops, sorry. So that will be 13.5. So this is 13.5%. That's the first region. Second region is 34. And third region, it's also 34. So that's 68. And so that's 81.5%. So the interpretation of this, the answer. So we know that 81.5% of the students in BCC, they are between, their age is between 20 and 21.5 years. All right, guys, you know what? So I'm gonna stop here, of course, because there is 1 minute left, and when I have time, of course, finish this. I will finish this next time. And as I promised, so next time we'll see how to find, this probability of X, but for for some random values. Okay. Thank you for listening, everyone, and I will see you on Wednesday. Take care, everyone.
Yeah. Thank you. Good night.
Good night. Thank you.
Thank you. Good night.
Good night.